Welcome to Econometrics B on binary responses. So before we kind of get to all the equations, let's just talk a little bit about where we see binary responses, because there's so many applications where you have binary outcome variables. Okay, so let's just, the binary outcome variable, that's a variable that takes only two values, 0 and 1, okay, or failure or success, okay, or do this or do that. Okay, and this appears in so many places, like an individual's decision whether or not to participate in the labor force. So that's, we're going to return to that and try to see if we can estimate a model that explains individuals' decisions whether or not to actually participate in the labor force. But a consumer's decision to whether or not to buy a car could be another example. There, it's like, you buy a car, y is equal to 1. You don't buy a car, it's equal to 0. If you can consider a commuter's decision whether to take public transport, a household's decision whether or not to move residence. If you move, y is equal to 1. If you don't move, y is equal to 0. High school students' decisions whether or not to attend college. If you attend college, y is equal to 1. Otherwise, y is equal to 0. And it's not only individuals' decisions or households' decisions we can model like this. It's also like firms' decisions. For instance, firms' decisions whether or not to enter a market, whether or not to invest, whether or not to export, whether or not to issue a patent. And of course, it could be whether or not to invest in something particular, like this latest state-of-the-art technology, or whether to go public with a firm to issue an IPO. All these things are binary responses, right? It could also be a decision of a student whether or not to take the exam. And so in the last example, right, maybe it is explained by some explanatory variables like, what is your ability? How much did you read the book? Did you see this video? And other explanatory factors that really triggers what is the probability of taking that exam or succeeding in the exam. So that's another binary outcome. Pass or fail. Okay. We're going to actually focus mostly on the first example with the participation in the labor force. There's a nice example in chapter 15 in the book, and we're going to try to see if we can replicate those results using some Python code. And in doing so, trying to really capture the one-to-one relationship between the equations in the book and the computer code, so that you kind of get a less abstract idea about what is going on. I mean, there's a lot of abstract math for second-year students. So we try to really take this down by simplifying with computer code. Anyway, so this is kind of the plan. We're going to start with modeling binary responses. So binary response models are really, I mean, there's not only lots of examples in their own right, they're also often used in combinations with other econometric models. So for instance, in this course, we will look at corner solution outcome models and sensor regression models and sample selection models. So in the latter example, in a sample selection model, you may have that you observe only the wages for people who work in the labor force. And in that sense, there's an endogenous selection into that sample. And that sample selection, is a binary choice whether or not to participate in the labor market. So there you got, as part of another model, a binary response model. Anyway, I'm not going to expect that you understand this at this point. I'm just trying to say that binary response models are really used in combination with other models to form more sophisticated structural models. It's also, can be used in combination with continuous choice models. It appears in duration models, where you would say try to model the duration in an initial state. Well, that's a little bit like, should I stay or should I go? Should I stay in the initial state another period? And then that's kind of a discrete choice. And for some specifications of duration models, you can actually you can actually reformulate them as discrete choice models. So so this is yeah, that's kind of the motivation. Why is this important? Okay, and it is really very, very useful. Okay, so why don't we just get through the equations right away? Okay, so the main object of interest, also because it's something we could potentially observe, that's the response probability. Okay, so the response probability, we'll call that P here. That's the probability that y is equal to 1. Okay, so what does this mean? This means that it's y is equal to 1 conditional on x. Okay, so that probability, the probability for example, participating in the labor market, well, that depends on a bunch of explanatory variables x. For instance, what is your education? How much experience do you have in the labor market? What's your age? What's your partner's income? Factors that potentially affect the outcome y, where the probability of participating in the labor force. Okay, so that response probability is a function of the explanatory variables. Okay, and we want to try to see if we can estimate that function. Okay, this requires to put more assumption on that we did right now, like what is the model for that response probability. So we can return to that. There's several different models we can look at. Okay, so here, just to get a little bit of notation straight, x, that's a vector of many different explanatory variables. So here you have k explanatory variables, so that would be so it'll be k explanatory variables. Okay, and here to begin with, we take all these variables to be exogenous. And so that's kind of the beginning. But later we'll actually look at how to deal with endogenous explanatory variables. But for now, we just take them as exogenous. Okay, so now it makes sense to see, okay, how does a change in those explanatory variables affect the response probability? And this is exactly what we have here for a continuous change in x, right? You just differentiate this guy up here, and then you get the partial effect for a continuous change. Now, of course, in order to really differentiate, well, you need to know what that probability is and how that is a function of x. And so we're going to specify a model for that. That could be a linear function. In this case, it would be the linear probability model, or it could be a nonlinear function. And we're going to look at both. Okay. For binary outcomes, right? So here, for instance, if you look at the changing the last one, so changing that, well, it doesn't really make a lot of sense to look at a marginal change in a binary variable, right? So here you may want to calculate simply just the difference between the response probability given that xk is equal to 1, and given that xk is equal to 0. And then you have to put in some other values for the remaining explanatory variables to in order to calculate that partial effect. Unless that probability is really a linear function, well, and separable in all the explanatory variables, then generally these partial effects depends on the explanatory variables. Now, this is something new to you because you used to do like linear regression models. If you take the partial effect of a linear regression model and differentiate with respect to, say, the jth explanatory variable, you're just gonna get beta j, the coefficient on that variable. That's the partial effect. So you have a constant partial effect. That's generally not true for binary response models that were, at least if we model them as a non-linear function in parameters. Well, okay, so let's kind of move on, right? We want to look at given that we now are interested in that response variable, we want to potentially look at what is the distribution of that response variable y. Okay, so what is the probability or the conditional distribution of y, conditional on x. Okay, so y is Bernoulli distributed conditional on the explanatory variables. Basically, there's just these two outcomes that it can either be 0 or it can be 1. So this means that the conditional distribution of y conditional on x is completely summarized by these two probabilities. The probability that y is equal to 1 conditional on x and the probability that y is equal to 0 conditional on x. Essentially, there's only these two outcomes. Okay? And since probabilities are must sum to 1, well, you can get the probability y is equal to 0 as 1 minus the probability that y is equal to 1. And so we can get the conditional distribution f simply by this expression. And now you see here conditional on y is equal to 1. Well, then you got, if you want to have the probability of y equal to 1, well, then this collapses to p of x. And in the other case, it collapses to y minus p of x, because with y is equal to 0, well, then you got a 0 here, and then you got basically 1 here. So this becomes 1 times 1 minus p of x to the power of 1. Okay, so and that's kind of a general formulation for binary outcome models. Okay, so we'll use that when we estimate the model with maximum likelihood. Then you can, for Bernoulli distributed variables, you can derive the first conditional moments as the conditional mean of y given x is equal to the response probability, which is kind of very intuitive, right? If you might just think about it, binary indicator y, it takes a bunch of values, 0 and 1. If you average over all those, well, you're going to get the fraction that are equal to 1. That is the expectation of that, right? So that's kind of very intuitive. The variance, that's p times 1 minus p. We can actually come back to this and talk a little bit more about it. Anyway, the key thing here now is how do we actually specify a model for p of x, or for the response probability, and estimate that model? Well, we need to impose a little bit more structure. Right now, we've really operated a high level of generality here. So we need to put some more structure on p in order to really estimate it. And what we're going to do is we're going to specify what we call a parametric model. Okay, so a parametric model would be that the probability is equal to some function g of the explanatory variables and some parameters, and then g would be known up to all those parameters. So once, if you were to know all the parameters, then for any value of x, you would fully know what the probability that y is equal to 1 is. Okay, so you would only need to know the parameters because you already know the functional form of g. Okay, so we assume the functional form of g. It may be that g is a linear function, it may be something else, right? And then once you got the parameters, well, then you can calculate the probabilities. Now, in order to really estimate the model so we can have an expression for the response probability, well, so that we can estimate those parameters, well, we need some data, right? And we assume here that we have a random sample of the binary outcome and the explanatory variables, and that sample size is n. So we have basically a random sample. So we assume that unit I is just randomly chosen. Okay. Of course, that's the ideal situation, but we're going to start with that before we make things more complicated. For estimation, once you have data, well, you have to think about identification first, but we'll come to that later. But given that if the model is identified, if we can actually with this things we can potentially observe, we can learn enough about beta. Well, then we can estimate beta by using those data by either, for example, maximal likelihood or on nonlinear least squares. So in case you want to do maximal likelihood, well, then you would have to use the conditional distribution of y given x. That would be conditional maximum likelihood, which is basically what we had before. Remember, we derived the conditional distribution as what we have here, right? P of x to the power of y, 1 minus p of x to the power of 1 minus y. Now we just have a model, right? So we just put in the model for p of x, And you see we get basically a model for the conditional density that depends now on parameters, assuming that we have specified the functional form for G, okay? So if we do that, and then we can basically estimate the parameter beta by maximum likelihood by maximizing the average of the log of the likelihoods evaluated in the data. So essentially, what you do here is you put in all the data points here, and then you evaluate what this function is. The sum over all the observations, that's a likelihood function, right? And then you move around the structural parameters, you move around beta, all so that this guy here on the right-hand side is maximized, okay? And that's just how you do it, okay? With nonlinear least squares, well, you can also estimate that, the beta with nonlinear least squares, because we have a regression model, right? Because before we found out that the conditional mean of y given x for a Bernoulli distributed variable was equal to p of x. Well, this is a nonlinear regression model. If G is nonlinear, it's a linear regression model. If it's if G is a linear function, okay? And so you can estimate beta also with nonlinear least squares. So you have different choices of estimators. We're gonna focus a lot on maximum likelihood because usually we can actually specify the entire distribution and it's more efficient. Okay, so we're still operating at a high level of generality. We'll be much more specific a little bit later, but this is kind of, you know, this is the cliffhanger for concreteness. Okay, so why, you know, which estimators you use? Okay, should you use like maximum likelihood or nonlinear least squares? Well, you know from Jesper that maximum likelihood, that's the most efficient thing you can do. It's basically using all the information you have on the conditional distribution y given x. But then you have kind of the problem that if you misspecify G, well, then you also misspecify this conditional distribution, right? So that's what we have here, right? It's this G is something that we assumed, and that assumption was wrong. Well, then if G is wrong, well, then our model for the conditional density is wrong, and you got a misspecified model, and you get inconsistent estimates, right? So you know, it seems like maximum likelihood is kind of you know, a little bit sensitive to assumptions about G. So we get potentially inconsistent estimates if G is wrongly specified. Why don't we just use nonlinear least squares, right? It's not specifying the entire distribution. So it may be that we could get the conditional mean of y given x, right? You know, if you make assumptions only on say the first moment and not on the entire distribution of y conditional on x, then that's kind of a weaker assumption, right? So I mean, when you make assumptions about the entire distribution, it's all the moments. It's not only the mean, it's also the variance, the, you know, skewness, kurtosis, and you know, all the other moments that specify the distribution. And therefore, sometimes we think that that nonlinear least squares is more robust than maximum likelihood. It's less efficient, but it's more robust. But really, it's not the case here. Because if we have misspecified the model for, we've misspecified our model for the response probability so that our conditional density here is misspecified, well, it means that G is wrong, right? And if you look back and we know that the conditional mean was equal to the probability, the response probability, well, you also got that wrong. So it doesn't really help you to do nonlinear least squares in this case, okay? And the problem really works through the model for the conditional density. So it's for instance, if you choose some linear function here and that is by no means a linear function, well, both the regression model is going to be misspecified and the model we're trying to estimate with maximum likelihood is going to produce inconsistent estimates. Okay, so if MLE is inconsistent, well, the nonlinear least squares is inconsistent too. So That's not always the case, right? Like, there's plenty of examples where we would think nonlinear least squares is more robust but less efficient. Okay. So I'm going to conclude this thing here, but just like a little teaser for the next video, because I'm going to stop here just to make give you time to breathe and have a coffee. We're going to talk about in the next lecture about how to actually specify G. Okay, so there's lots of popular specifications here. The easiest one is just assume that G is a linear function. Okay, in which case you would have the linear probability model. So that's what we're going to start talk about in the next video. This is very, very easy because you can estimate essentially this model by OLS. Okay, and OLS for that linear model is equal to maximum, like it's identical to maximum likelihood. You can then after that this turns out this model has some issues. For instance, it predicts the probabilities outside the unit interval. I mean, if you think about beta being positive, you increase x. Well, if x gets big enough, well, then you have a probability that could be, certainly be outside the unit interval because of the linearity. So that's kind of that's an issue. There's some other issues about heteroscedasticity and so on. We'll talk about that in the next lecture. Then, in order to accommodate this problem, where we have a very popular class of models called linear index models that includes the so-called probit model and logit model that we're going to spend a lot of time going through in the lectures after that. And then, of course, you can have more flexible parametric forms. You don't have to have, I mean, in the linear index models, what you would have is you would put basically some x times beta inside a linear function that maps these probabilities into the unit interval. So you're always sure you have probabilities between 0 and 1, but it doesn't have to be in that way. It doesn't have to be a linear index that enter in there. You can work with this general specification. You would just have to specify it if you want to have a parametric model. And then there's something called a non-parametric model, where you would not only try to estimate parameters, but try to estimate the entire functional form for G. So we'll leave that to the future. For now, it's just about talking about how to actually model the linear probability, the probability with a linear index, and we're going to do that next.